This is the video lesson for 5.1 Statistics class at Pulaski Tech. John Allison's instructor. In the last chapter, in chapter 4, we talked about discrete probability distributions. Today you're going to be introduced to the normal distribution, which is a continuous probability distribution. If you recall from before, a discrete probability distribution, a random variable x had a finite number of values that it could take on. In a continuous probability distribution, a random variable x can take on any value in an interval. In a discrete probability distribution, like the rolling of a die, a six-sided die that we talked about, your random variable x could equal 1, 2, 3, 4, 5, or 6. A fixed number of possible outcomes. In a continuous probability distribution, your x can take on a value between any two numbers in an interval. For instance, it could take on anywhere from 10 to 100, just depending on what we're working with here. The normal curve is the graph of a normal probability distribution. Our discrete distributions we graphed with histograms, but a continuous distribution is graphed with a curve. The normal curve is always going to be a bell-shaped curve with certain properties. The mean, median, and mode of a normal probability distribution are all equal. The normal curve is symmetric about the mean. That means if this graph were on the x and y axis, there's a line of symmetry, an axis of symmetry, straight down the middle, and that x value is the mean of this probability distribution, where half of the curve lies to the left of the mean and half of the curve lies to the right of the mean. If you could fill in the area under the curve and measure that area, I can't color in underneath there between the x-axis, but if you could go all the way to the left and all the way to the right, that total area under that curve is equal to 1. And lastly, this graph of the normal probability distribution never touches the x-axis. As you move to the left and to the right, it gets closer and closer. It approaches the x-axis, but it never touches. So the x-axis forms a horizontal asymptote for this normal distribution curve. The graph of every normal distribution, or every normal curve, has the same general shape. Bell-shaped. But is unique depending on its mean and standard deviation. Recall, the mean we represent with mu, the standard deviation with a small sigma. The graph of the normal curve above has a certain mean and a certain standard deviation. If we sketch another bell-shaped curve, a normal curve, but this one is shorter and wider, centered to the right. This is the graph of a normal distribution. What we know is its mean is larger because it's to the right on the x-axis than the mean of that first one. And we can tell because the graph is spread out further that the standard deviation of the green normal curve is going to be greater than the standard deviation for the red normal curve. Because remember, a bigger standard deviation means the distribution is spread farther. In a normal probability distribution, the area of a region under the curve, sketch one, this is what we mean by the area of a region under the curve. The area of the region under the curve is the probability that your random variable x lies between the endpoints of the interval on that x-axis. In this case, between x1 and x2. In the notation we used in the last chapter, that would be the same as saying the probability that x1 is less than or equal to the random variable x is less than or equal to x2. Remember, the entire area under the curve is equal to 1, so the probability that negative infinity is less than or equal to the random variable x is less than or equal to infinity, the extremes left and right of the curve, is equal to 1. Recall too from our bell-shaped distributions we studied in the past that the probability that your random variable x lies within one standard deviation of the mean, or from the mean minus one standard deviation, is less than or equal to your value x, your random variable x is less than or equal to your mean plus 1 standard deviation, the probability that the random variable x lies within 1 standard deviation of the mean is approximately equal to 68%. The probability that it lies within 2 standard deviations of the mean, or the mean minus 2 standard deviations, is less than or equal to the random variable x is less than or equal to the mean plus 2 standard deviations, is approximately equal to 95%. And the probability that your random variable x lies within 3 standard deviations of the mean is approximately 99.7%. The standard normal distribution is a special normal distribution with the mean equal to 0 and standard deviation equal to 1. Even though I'm not an artist, this is supposed to be symmetric, so you have to pretend that it is. Recall from our previous study, when we were doing bell-shaped distributions, that we could convert any random variable x to a z-score using z equals x minus the mean divided by the standard deviation, and that z-score measures the number of standard deviations the value x is from the mean. A z-score of 1 means that the random variable x has a value 1 standard deviation to the right of the mean, 1 standard deviation greater than the mean. A value of a z-score of -1 means that your x has a value that is 1 standard deviation to the left of the mean. -1.5 for a z-score would indicate that your random variable x has a value 1 1/2 standard deviations to the left or less than the mean. If we want to find the probability that x lies in an interval using z-scores on the standard normal curve, say we want to find the probability that z is less than or equal to 1. We can use our calculators to find it. On the curve above, that is, what we're really finding is the area under the standard normal curve from -infinity to 1. That area represents the probability that our z-score for our random variable x is less than or equal to 1. To do this, we're going to use our calculator and we're going to use a normal distribution function on the calculator. What you'll see on the calculator screen is normal CDF and when you enter this in the calculator, you're going to put a lower bound for your interval, comma, upper bound for your interval, and close parentheses and hit enter. To get to the normal CDF on the calculator, you're going to hit the second button, then the vars to get the distributions to come up. Normal CDF is number 2. Scroll down and highlight. There should be an A here. Now, because this curve extends to the left to negative infinity, what we are going to enter is negative 10,000 to represent negative infinity. That's far enough that your calculator won't know any difference between negative 10,000 and negative infinity. Because we want a z-score of 1, our upper bound is going to be 1, as indicated on the graph above. When you enter that in the calculator, your value is approximately 0.8413. If you want to find the probability that z is greater than or equal to, let's do 1.25. Let's go back up to the curve and let's look and see what region we're talking about here. Greater than or equal to 1.25. 1.25 is approximately here, so we would be looking at the region under the curve from 1.25 to infinity. Again, because we can't type infinity on the calculator, we're going to find normal CDF. Our lower bound this time is 1.25. We're going to use 10,000 for our upper bound. Normal CDF 1.25 comma 10,000, and we'll get 0.1056 or 10.56%. We can do the same thing if we wanted to find the probability that z was between let's say negative 1.5 and 1.25. Between negative 1.5 and 1.25 would be the area under the curve between those two values, where negative 1.5 would be our lower bound and 1.25 would be our upper bound. And so in the calculator we'll put normal CDF negative 1.5, 1.25, and see that the probability is 0.8275 or 82.75%. So let's look at how we can use this. If we have a life expectancy of a certain breed of dog, normally distributed, with a mean of 14 years and a standard deviation of 1 year, I'm going to start by sketching a curve. It's a normal distribution, so it's a bell-shaped curve. the mean is 14 years. One standard deviation is 1 year. Using z-scores, we can convert this to a standard normal curve, and we can find the probability that a dog of this breed lives less than or equal to 12 years. To do that, our random variable is 12, so we want to get a z-score that's going to be equal to x minus the mean divided by the standard deviation, in this case 12 minus 14 divided by 1. Negative 2 divided by 1 is just negative 2. So we want the probability that our z is less than negative 2. So we do normal CDF. We're going to do negative 10,000 because we can't type in negative infinity to negative 2 and find the probability. 0.02275, we'll say 0.0228. So that means the probability that this dog lives less than or equal to 12 years is 2.28%. If we want the probability that the dog lives less than or equal to 14 years, we're going to find z-score for 14. Remember, x is 14, or the mean is 14, so our z-score should be 0. The mean of the standard normal curve is 0. The mean of this curve is 14. So when we do x minus mu divided by the standard deviation, we get 14 minus 14 divided by 1, which is 0 divided by 1, or 0. Because the area under the curve to the left of the mean is half of the curve, then this probability should be 1/2. So let's do the normal CDF. Lower bound, we're going to set at negative 10,000 again. Upper bound at 0. And we should get 0.5. We get 0.50000, a whole bunch of zeros and 5, which is 50%. We want the probability now that we lie between 13 and 15 years. So in this case, it's pretty easy to figure out because our standard deviation is 1 year and our mean is 14 years. So our z-scores are going to be negative 1 and 1. But if this had been anything but even numbers of standard deviations, we would have to find standard deviation, or we would have to find a z-score for both of them. So your x1 here would be 13 years, or x2 would be 15 years. We would have to convert a z-score for both. So we would get z1 is equal to 13 minus the mean of 14 over 1. z2 is 15 minus 14 over 1. z1 would be negative 1. z2 is 1, just like we said it should be. So what we're finding is the probability that negative 1 is less than or equal to z is less than or equal to 1. Because this is a bell-shaped curve, this should be somewhere really close to 68%. We're looking for the area under the curve between 13 and 15 within 1 standard deviation of the mean. So here we're going to do normal CDF, negative 1, 1, and we should get something really close to 68%. And you'll see you get 0.6826 or 6827, so 68.27 or 26%. Now let's look at one greater than 15.5 years. Here our x is 15.5. Convert to a z-score. 15.5 minus 14 divided by our standard deviation of 1. That's going to give me 1.5 over 1 or 1.5. So what we're looking for here is the area under the curve to the right of 1.5. The probability that 1.5 is less than or equal to z. From 1.5, we're going to use 10,000 for infinity. And see, we get 0.0668. So 6.68% is the probability that one of these dogs will live to be more than 15.5 years.